Kieran. Yes, I had the advantage that the previous speakers introduced quite well some of the key concepts of constraint programming. So that'll save me time, but I'll try to relate back to these talks when I can. So here's the plan of this talk. So I'll first, again, make the point that we've got exposed combinatorial structure from the high-level models in CP, and that can be very useful, as Oz mentioned before and argued for. And I'll focus on new, well, relatively new things that we can do from those constraints, that structure. So namely counting and weighted counting. You'll see why when we come to the third part about the CP-BP framework. So basically CP solvers where you mix it with belief propagation because you've got a richer propagation medium. I'll come to that and give you some examples and why that can be useful. Okay. So one could say that among the model-based combinatorial solving paradigms, CP sort of took the road less traveled. Most other approaches, SAT, integer programming, I would imagine ASP as well, I think, have models with typically lots of constraints in a simple syntax, and lots of them, whereas CP tends to have more concise models, but with more heterogeneous syntax for those constraints. And so each constraint represents a bigger chunk of the problem, as you've seen in some of the previous talks. Okay, here are two example models. The first one, a round-robin tournament, where you're defining some variables, and some constraints are simple. You've got even unary constraint here, and so the binary constraints. But most of the combinatorial structure of your problem is represented in those global constraints or larger arithmetic constraints that, such as the all different here. So you have several all different constraints and regular constraints. You'll hear about that later on. That's where your structure is, and maybe you can exploit that. We do actually. I'm proposing to go even further. Another example here where you're moving furniture, so scheduling problem. Really, you have two resources, handlers and trolleys that you need to use. And again, most of the problem, I mean, this is the whole model. Most of the problem is represented by these cumulative constraints. John mentioned this morning cumulative scheduling. So that's a big chunk of your problem is represented there. Okay. So I would argue again, maybe, that the distinctive driving force of CP is this direct access to problem structure from the high-level modeling that we use. Okay. In the end, we may be using, a SAT solver possibly or something, but you start off with a high-level representation, and that gives you or gives CP sometimes an edge in how to solve the problem. How does one identify, nominate these high-level constraints? I would say that over time, looking at applications, you identify structures that are complex enough to provide structural insight, but that are simple enough that the tasks you want to perform on them are tractable most of the time. And there are some exceptions, but that's typically how you decide, okay, this would be an interesting constraint that we can use in different problems to solve different problems, to express, to model these problems and then solve them. What sort of thing do we do with these constraints? Well, traditionally, as Kieran said, at least you want to know, given a constraint C, is there any solution to that constraint? Or is this a solution to the constraint? The domain filtering, the arc consistency that you heard about, we're asking, is there any solution to the constraint, so at the constraint level, such that variable X takes value D? So is that assignment supported, or should it be removed from the domain, as you saw in previous talks? And other things, what I want to focus on are these questions. So how many solutions are there to C? So you want to count the solutions, or even more so, how many solutions in which X takes the value D? Okay, in what proportion of these solutions? And that can also be quite interesting to compute. Okay, simple example here. let's say you have a binary constraint, okay, over variables x and y. That grid here, every row in that grid would represent a value, possible value for y, and a column, a value for x, okay? Let's say that you've got the green dots represent the solutions to that particular constraint. So if you have, so you may have an initial domain for x, that's a blue segment here, interval, one for y. One way to look at domain filtering that we do, the inference that we do, is, well, you're projecting these solutions along the axis, and you get the reduced green intervals here. So you get a subset saying, okay, these values are supported. The others are not. There's no value for x. There's no solution using this value for x. So it could be filtered out. So that's what you want to do ideally, typically in CP. Okay. But that's only part of the picture. With the same, so consider a totally different set of solutions here for another constraint. This one, it has exactly the same support. Okay, projections are the same. So if you just look at that information, the outside information you get from projecting from the domain filtering, you don't really distinguish between the two sets of solutions, the two constraints, really. Okay, well, what if we worked a little bit harder and computed the frequency counts over the values? Okay, so now these are the supported values, but this occurs 3 times in 3 solutions, this in 3, 2. So you get a discrete distribution over the domain. So now all of a sudden you're getting more information instead of having, okay, these values are possible, but from our perspective, equally likely. Here, you're getting additional information. Well, this one is maybe more likely to be useful because it is very popular. It occurs very often in an assignment to this, a solution to this constraint. And actually, for example, you could use the mode of a distribution as a branching heuristic, saying, okay, let's try out this value. Okay. So that's the type of thing that we want to compute. And well, so the other constraint here would have a different distribution in different modes. So you're distinguishing these 2 constraints here. Okay. Technically, what you want to do is to count solutions. Here you want, for example, to know that, well, 5 out of 22 solutions use this value. Okay. So you want to count solutions, and that's why I'll spend some time here looking at counting and weighted counting. You have to trust me at first why we want to do weighted counting. It'll become clear later on. And I'll give you examples of constraints, illustrating 4 of the techniques we've been using so far to perform the counting. Okay. So again, the initial, we start from a constraint is something that traditionally what we want to do is tractable, is easy to do. That's maybe the inference for the domain filtering. Maybe sometimes it's the same thing for counting, maybe not. So as we will see. Okay. So the first case is where we're fortunate in that we have a compact representation of the set of solutions to a constraint. I'll use a particular constraint, the regular constraint here, but and you'll see similarities with exact decision diagrams that John mentioned this morning, where there was a compact representation of potential. So polynomial size of potentially an exponential number of solutions, because basically you're sharing edges. Okay, I'll recall that, but let me first define what the regular constraint is. It takes its name from regular languages, so automata here. So that regular constraint over a finite sequence of finite domain variables, x1 to xk, it holds if that sequence spells out a word recognized by the automaton, by the regular language. Okay. So for example, I've got the automaton here. I'm using 7 states, initial state 1, and I'm using colors to represent values. So on the value red, you go from state 1 to state 2 and so on. I think everybody's familiar with automata. Okay. Now, what do we do for filtering here? Because I'll just mention that because we'll see that we don't need much more to do counting. It works as follows. So you start with the automaton here, and you build this DAG. So you've got layers of nodes here in your DAG. There's one layer per, in between. The number of layers depends on the number of variables, really. So you've got a variable identified with the transition from one layer to the next for every variable. And here are your states of your automaton. And you're basically on, this is the, say the domain of the variable. So X1 can take value red, green, yellow, so forth. You're unfolding the automaton over the domain there, over the sequence of variables. So you start, initial state is 1. So on value yellow, you stay at 1. So you do a straight edge. On value green, you go to state 3. So that's there. And so on. You extend from there all the way to the end. That's the forward pass. And backward, notice that, for example, here, this does not lead to anything in the last layer. So there's a backward pass you clean up, and you get something that looks a lot like those decision diagrams if you look at it sideways, okay, here, basically. And it has the nice property, again, as well, that there's a one-to-one correspondence between paths from the initial state to the last layer and solutions to your constraint. Okay, you've got a compact representation, and you may not have noticed, but between this, so when you do the backward pass, you had the green value was possible for many variables, and it can be filtered out because the corresponding arcs don't appear anymore when you clean up. Okay. Now, but you really want to do counting on this. So how do you do it? So you've got this layered graph. Well, you just need to work a little bit harder. You maintain some information at each node, a pair of numbers. So the number of incoming paths from the initial state at a node, and the number of outgoing paths to the final state, to a final state. Okay. So for example, here, that means that there are 2 incoming paths from the end, there are 2 outgoing ones. Okay, from there. There's one there and there's one like that. Okay. That's an easy recursion to compute that. So that's not much effort. And once you have that, well, if you want to count all solutions, as a side effect, if you look, for example, at the initial state, you could look at the final states as well. Well, you've got 19 outgoing paths to the final state, so you've got 19 solutions. Okay. What if I really want to know, well, how many solutions is X3 taking the value red? Okay, you want to compute this marginal bias, depending on the terminology you're familiar with. So I'll notate this as theta of X3 of red. Well, you've got 19 solutions in all. What do? You look at the arcs corresponding to the layer for X3 here. You look at all the red arcs, and you want to know how many paths go through one of these red arcs here, corresponding to a value of red being assigned to X3. Well, so you look at this is the first red arc. You take the endpoints. Incoming is 1 times outgoing is 2. That's 2. Then the second red arc, incoming 2, outgoing 2, 2 times 2, that's 4 in all, and so on. And so you find out that you've got 10 over 19 solutions using value red for variable X3. So you can see this as being the marginal probability of X3 equal red if a solution is selected uniformly at random. Okay, so the good news is that it doesn't cost you much more here. Okay, if you're doing the work for filtering, counting, costs you almost nothing more. Okay. What if you want to do weighted counting, for reasons that will become clear later on, as I said? Well, basically, you change. So each arc now has a weight. It's not on the picture, but and the weight of a path is a product of the arc weights. Okay. Well, you just maintain different information, maintain the sum of weighted incoming paths and the sum outgoing paths, and there's a small change to your recursion, but basically it's not harder to do that. Okay. So that's when you're lucky. It doesn't cost you much more. You already have a compact representation of the solution set. but you don't necessarily have that. Remember the all different constraint? You've seen this a few times already. So all the values taken by these variables must be different. You've got this value graph, variables on one side and values on the other, and you were told, it's equivalent to looking at for a complete matching. You can also view it on the adjacency matrix. So you're looking to pick a 1 in every row such that they're in different columns, okay, equivalently. So this matching here in red would correspond to these ones being selected here. Okay, very useful constraint. We know that it's domain filtering doesn't cost you much, as you've seen before. Okay, great. But counting solutions costs you significantly more if you want to do it exactly. So the number of solutions, and one speaker alluded to that, I forget who, it's the same. So it's the number, you're looking for the number of perfect matchings in a bipartite graph. That's equivalent on the adjacency matrix to the computing the permanent of that matrix. And that's hard. I think someone said actually that it was Sharpie. I think Kieran maybe. So it's a Sharpie complete problem. So you're out of luck. So you can't solve it efficiently under reasonable theoretical assumptions. So what do you do? Well, fortunately, it's a well-studied problem, the problem of the permanent. So there are known estimators to compute it. Here's one, and I think it'll be easier. I'll just show you an example of how it works. But it's basically looking at the ones in a row, goes row by row, looks at number of ones, picks one uniformly at random, and computes it recursively, but computes a product of the number of ones that are in every row. So example here. So first row, you've got 3 ones. You pick one at uniformly at random, for example, this one here, the 1, and you note here that you had 3 ones. You go on, well, you remove that row, you're done, and you remove the column. You can't pick ones in that column anymore. And then next step, well, there's only 1 1, there's no choice. And then there's only 1 1. That's the only one you can pick. Again, here you go to choice between 2. Let's say you pick the last one, and you're done. And you take the product, and it gives you an estimate of the number of solutions. Happens to be the exact one here, but that's a very small problem. So that estimator, it works well according to us. So it works well for almost all dense matrices, not so much for sparse matrices. Poor results in some special cases of dense matrices. This one, the upper triangular one, you may notice that there's only one solution possible. I mean, this one doesn't have any choice, so this one will have to take. So these are the values on the diagonal, but the estimator will fail most of the time, right? Because it starts with the first row and picks one at random. If it picks the wrong one, they're done. Okay. Well, what we do here, we add domain filtering. So you have the estimator here, and you just add, before picking one of the ones, you add domain filtering to rule out these possibilities, and that helps quite a bit. Helps avoid the dead end, so improves the estimator, and then we can use that estimate as for a number of solutions. And when you want to do the marginals, the proportions, well, we can look at the ones that have what we're looking for. So from our sampling. Okay, so that's another approach we use for in some cases. Oh, in the weighted case, again here, not much more difficult. So your entries are now non-negative, and you are choosing randomly, but according to the distribution given by the weights, basically. And here you're not multiplying by the number of ones, well, you're multiplying by the sum of these non-negative entries. Okay, good. Now we can also use in some cases some existing theoretical result. Let's stay with another approach. Let's stay with the all different. The sampling can still be expensive to do because you have to do it, if you do it at every node of your search tree, it can get to be expensive depending on how many samples you're collecting. I told you the permanent is a well-studied problem. Well, there are also known upper bounds on the permanent, on the 0, 1 for 0, 1 matrices. So in the case of the unweighted case, and they're pretty simple. They rely on the number of those are the expressions on number of ones in the rows. I don't want to go into the details, but they're fast to compute. A lot of these functions can be pre-computed. So that's the good news. And even in the weighted case, where you've got some non-negative entries, there are also known upper bounds. Okay, with these things can be, I'm going to give you a function g here, but that can be pre-computed. So that's fast to use. But I really want to tell you about another constraint and a nice theoretical result here, the spanning tree constraint. So you're given a graph, and you have a set variable, so t, which is a subset of the edges of your graph, and the spanning tree constraint asks that t must be a spanning tree of G. Okay, very standard. So given the graph here on the left, this is one example of a spanning tree for that graph. And if you want all of them, here are all the other ones. Okay. And I've put some edges in color because, well, you're interested in, okay, how many spanning trees use the yellow edge, or how many use the red edge, for example. Okay, can I answer that question? And so here's where theory comes in. So there's a nice theorem called the matrix tree theorem that we can use. So first, given a graph, we can use a matrix representation called the Laplacian of that graph. Basically, you can look at it as being the adjacency matrix, where instead of a 1, you have a -1. And on the diagonal, you have the degree of the vertex. Okay, so here you've got an edge. The red edge is represented between V1 and V5 is represented here. And in terms of degree, the endpoint here, V1 as degree 3 and V5 as degree 2. Okay. So the result is that any minor of the Laplacian, so you remove one row, one column, take the determinant, any row, any column. Any minor is equal to number of spanning trees in absolute value. Okay. So for example, here, I've taken out the first row, first column, take determinant, 21. Trust me, there were 21 spanning trees before. Okay. So it's easy so it's relatively cheap. It's a determinant computation to get the number of spanning trees. All right, that's a very cute result. But we're interested in, even more so in counting solutions involving an edge. So here, it'll be easier to say solutions excluding a given edge, and we'll come back to including it afterwards. So I want to know spanning trees from graphs where I remove 1, 5 with respect to all the spanning trees. That's the Laplacian for your graph G. That's the Laplacian where you move this edge. Well, only 4 entries change, the green entries. Those are the only one that's changed, the degree of the endpoints and the edge. And these 4 entries, even if the matrix is very big, the graph is very big, they are in 2 columns and 2 rows. Okay. So I'm interested in taking a minor. So if I take the minor and I remove, one of these rows and columns where those changes appear, then I'm left with something that's very similar to the original Laplacian. It's only 1 entry that's different. Now, okay. So I'm computing a determinant of something that's almost the same matrix. There's 1 entry different. Well, there's a formula for this that says that what's the determinant of this matrix that's almost like M? Well, it's related, but it's from that to the determinant of M. So, and in our case, it simplifies to 1 minus the jth entry on the diagonal of the inverse of matrix M times the determinant. Now remember that we're interested in that ratio. So that's this over this, the determinant disappears, and you get something very elegant, I find. And that's for excluding the edge. So if I want to count know the proportion of including that edge, it's 1 minus that, so it's this. So you need to invert the matrix of the Laplacian and look at the entries on the diagonal. Okay. So for example here, so you've got this graph. So you basically you need to do matrix inversion for one matrix inversion for all the edges incident to a particular vertex. So you do that. So if you have a vertex cover, maybe you can that gives you how many you need to do. So for example, in this graph, if I invert it, I see that the yellow edge appears in 12/21 spanning trees, the blue edge in 10/21, and the red edge 13/21. So matrix inversion, and you're counting the proportion. So very good. I'll go quickly over this because it's also very nice. What about minimum spanning tree? Okay. So now your edges have weights. And here are all the trees of cost 5, cost 6. You do something similar, except that your Laplacian is generalized. So here you don't have -1s, you have so you've got polynomials in univariate polynomials here. You've got -x to the power determined by the weight of that edge. The degree, well, is the sum of so you've got d1 is degree 3, but it's got one edge of weight 2, 3, 1, so it's x2 plus x3 plus x1. And if you apply the same theorem, something beautiful happens. So if you compute the determinant, you get this one here. And then that sort of spells out. So you look at the lower degree term. So each monomial here, each term, that tells you, the coefficient tells you how many spanning trees, and the exponent, the cost of the tree. So you've got 3 spanning trees of cost 5, 6 of cost 6, and so on. So quite pretty. There's the Kirchhoff. And here, so in practice, we don't compute those determinants over polynomials. What we do is we fix x, some value between 0 and 1 that sort of favors lower cost trees, and you fall back to the scalar entries, and you do that as usual. Okay. Okay. Domain relaxation. A few words. Knapsack constraints. You've heard about those before. We could do them as regular as decision diagrams. Thing is, it runs now in pseudo polynomial time. It's sensitive to the magnitude of your bounds, the numbers here, L and U. So you could do that if the numbers are not too big. Otherwise, while you could, in a nutshell, you basically relax the domains to intervals and assume that the values are uniformly distributed. And since you're looking at a sum here of random variables, say from uniform distribution, you get a nice normal distribution. You can use that as an approximation. Okay. I really want to get to this part here. So I've been telling you about counting, weighted counting. What can we do with that? Okay. So I want to move beyond standard support propagation. So what we call constraint propagation, but you're basically propagating which values in the domains are still supported. And I want to move to propagating beliefs or marginals. Okay, what is this picture? The blue rectangle and the red rectangle are two constraints. So the blue constraint is on variables x, y, and z, and the other one on x, y, w, and z. And you have the domains a, b, c, d, e, and you've got this discrete distribution, the probably mass function over the domain. So that more informative. Let me see information that's redundant. Okay, so you want to propagate that information. So saying that, okay, instead of propagating that C is not supported, I'll say, well, my belief is that the distribution over the domain of X, so as to which are good values, is such. The red constraint says the same thing, but going, well, something different the other way. And hopefully you iterate, and hopefully you get to maybe some agreement or converge to something, or okay, to get more of a global picture. And that corresponds to, you need to the weighted model counting to do this. An example. So that's a simple problem. You've got constraints over variables A, B, C, D, domains 1, 2, 3, 4. 3 constraints and all different, a sum and a binary inequality. If you apply constraint, if you do some filtering here, trying to do some inference in standard way, nothing happens. The domains are still keep all their values. Okay. What we want to do here is say, okay, I want to compute the marginal for value for variable C in the blue constraint for value 3. Well, this is simple. We can do it by hand. So there are 2 solutions that support C taking value 3. D should take value 3 or 4. Okay, so these are the 2 possibilities. So equal weight here. So I've got 2 out of 10 possible solutions. This given the domain. Okay, so that goes into a big. So I do this for every variable, for every constraint involved. So you can fill out this big table and notice that, for example, for variable D, the black constraint, the sum says, well, value 1 is a good choice, 10 over 20, but 4 is a bad choice. The blue constraint says the opposite, 1 over 10, 4 over 10. Okay, saying, oh no, so they may disagree. That's why you want to propagate the information and readjust. So you compute this. So a variable will take the point of view of each constraint, you multiply it, normalize it, and you get the current marginals, current beliefs for as to its values. Okay, that's so you do that for every, so after one iteration, you have something like this. Then it becomes more interesting. You do it again, but now, so you recognize this, but now the solutions don't have the same weight because according to the black constraint, D taking value 3 occurs in 3 out of 20 solutions, value 4 in 1 out of 20. So those are the weights. That's why you need the weighted counting. Solutions are not weighed the same through this iterative process. And then you get eventually, say here in 10 iterations, you get these. So then a pattern starts to emerge. It tells you that, well, it's very, according to the computation, very likely that C and D will take value 1. And about half and a half, values 2 and 3 for A and B. That's actually, in this simple case, very close to true marginals. There are only 2 solutions. You may have figured out already, 2, 3, 1, 1 or 3, 2, 1, 1. Those would be the true marginals. So about 50-50 here and 1 there. And that's what we had. Okay, so you're getting more information. You can iterate, and that can help you get a better picture of where the solutions are. So you can use it to branch for combinatorial search. And we've done that. I've alluded to that before, talking about the mode. So we typically do binary branching in CP. So xi takes value dj, or xi does not take value d sub j. You can do a number of things with that information. What we currently like is doing min entropy. So how do we choose the variable? So these are generic ways, automated ways of choosing where to branch next. Okay, so picking your variable. Choose a variable minimizing the entropy of the marginal distribution over its domain, because it makes sense. The lower the entropy, the more certain you are. You should be certain of what's going on. Okay, less uncertainty there is. Disorder. So that's picking that variable, and then, well, then for that variable, you choose the value maximizing the marginal with the highest belief. Okay, that was talked before. Well, for value selection heuristics, there's not. It's true that there's way less wisdom so far. That brings an option to distinguish between values and deciding what to branch on next. Okay. Near uniform sampling. Okay, so you want to sample solutions of your solutions or models, depending where you're coming from, of your CP formulation or model. Uniformly at random. Well, if let's say you compute, you're given the true marginal distributions again. So hopefully you get something close, but there are no guarantees really. So you're not, you can't, unless the constraint graph doesn't have any loops. I mean, there are some characterization, but that rarely happens in practice. What helps us here with respect, and I should have mentioned that with respect to standard belief propagation, is that our constraint graph, get a factor graph if you prefer, has fewer cycles, because a lot of the small cycles are sort of encapsulated in those global constraints. So that's one big node, the big factor, depending on, okay? So it tends to behave better. If you decompose it all different, it won't converge easily as well as what I've shown before. Okay, so you could say, well, I pick any variable, I pick a value according to the marginal distribution, which if it reflects accurately, reflects its how it appears in solutions, readjust distribution and repeat. So that potentially can help you do sampling. And okay, and last is something that we've started looking at, Neurosymbolic AI. So situations where you've got, so you're using neural networks, but in contexts where there's hard or deterministic structure, combinatorial structure that you need to respect. Okay, there are some applications, some examples where that's very important, and that's typically can be quite hard to learn. Can we use a model-driven approach, one of our models of that structure, CP or something else, to help either train or tune whatever the neural network will output? So combinatorial solvers in general can tell you whether or not it satisfies the constraints, but that can be expensive to run. CP can go a little bit further in poly time, typically just saying, well, this value is not supported, so it should be filtered out. With the marginals added on, well, so you get a distribution over the domain, the possible values, and that's sort of it's much more natural to integrate it within your neural networks. I'll give you two examples. And it runs, so it's something that you want to do in poly time as well. Okay, so I've taken this picture from another project, but let's just look at this box here. So this box here is a neural network. It's a generative model, so it outputs it's a sequence of tokens, of values. And typically it would, so it learns, this is during inference here. So it outputs a probability distribution, and it will sample every step. It samples from the distribution for the next token. So that distribution is different from one token to the next. The idea here is that, well, since now our CP-BP solver is used to manipulating distributions over domains, well, we just input that into our solver with the constraints, and it outputs a modified probability distribution from which you then sample. That will reflect what was learned from the training, the corpus, but also what you can do or what should do according to the constraints. Okay. We've used it also. Yes, that's the output. Yeah, I've showed you that. Okay. And we've also used it, I started using it for training here. It's a reinforcement learning framework where you've got a trained RNN, and the agent is being trained to fine-tune what has been learned. And here we can easily, since we've got these marginals, approximated marginals over the action or the value, well, we can use that from the CP model to add to the reward function. My apologies if you're not familiar with the reinforcement learning, to the reward function to help train the agent further. So it's just, it's information that's more natural to integrate into neural machine learning than just saying, well, it's the binary, it satisfies or it doesn't, basically. Okay, so to conclude, so again, my message, why does CP stand out? I think it's that direct access to problem structure from the start, high-level constraints in the model. And the more you can do with these, the more opportunities you may have. So we can do, well, I haven't talked about it, but we could do stronger search space reduction, so higher levels of consistency, better guidance to find solutions. I've mentioned that. Possibly sampling, natural interface with neural networks, and possibly even more. Okay, that's all I have to say. Thank you.
I can just.
It's for the people on Zoom.
That's why they're people on Zoom. So
I was just going to ask if there had been any formal analysis on the relationship between marginals and optimal solutions for optimization problems.
No, so all that I've said really holds well for satisfaction problems. Now for optimization, so you've got, well, we've done some work where one thing you could do is, let's say you're maximizing, set a lower bound and saying, I'm only interested in solutions that are at least as good as that, and compute marginals for that. Well, I won't go back to that, but the minimum spanning tree, you sort of get these marginals that are weighed by the quality of the solution that they're in. So so in some instances, there's potential to get information sort of that's about optimization as well.
Yeah, I guess so. For optimization, when you impose the bounding constraint on the objective, these branching rules are helping you find a satisfying solution for that subproblem faster, right?
Right. Yeah, that's it. You would focus. You would be directed toward these better solutions. Right. Yeah.
Kuldeep had a question.
So for the counting queries, it looks like you need something incremental, or are you, after every decision, do you just?
Oh yes. Okay. Good question. So this is information that you could do at every node of your search tree. Now it's potentially expensive in some cases. So what we've started doing is saying, well, if the search space hasn't changed so much, measured in a simple way, if the domains of the variables haven't changed so much, well, you're likely, probably you won't, the computation, you'll compute something that's similar to what you had before. So you just reuse these marginals, go down, and then when you decided it changed sufficiently, then you can recompute. Yeah, because there is always that trade-off, right? You're working harder at a node of the search tree to try to prune your search tree, have a smaller search tree, but in the end, if you look at runtime, there's this compromise.
Just to follow up, are you able to reuse the information of the marginals you had, few nodes above, or you just redo fresh calculation?
Oh, let me think. Yes, no, yes, I am reusing it. Yeah, yeah.
So you mentioned about dense sets of solutions for which you can do the counting, right?
There was in the context of the all different, the estimator, right? For dense matrices, yes. Yeah.
So what do you do for sparse sets?
Okay, yes, I should have mentioned it. So remember, we added domain propagation to the estimator that took care of the bad special case of the upper triangular matrix. It also helps you quite a bit on sparse. I didn't show you some graphs, but it improves it quite a bit of spending the extra time to do the domain propagation at every step, and you get a much better estimator. So for the sparse case, is not an issue once you have propagation, but still you need to sample. So that's in practice for the all different. If the number of variables is not too big, we compute the permanent exactly, but after 5-6 variables, you don't want to do that. And otherwise you use the upper bounds that I mentioned. And because we're taking the upper bounds are not so good, but remember we're taking a ratio of two things, and it sort of cancels out the badness. So in practice, so relatively to one another, the bounds are the value you get is pretty good.
And how much does it scale to, like, constraints with how many variables?
Oh, you mean in all? Well, depends very much on the problem. I mean, it is a bit more expensive to run. So what really kills it currently is problems where you have large domains. You've got some variables that's large integers, that because you need to maintain and compute information for every domain value. If your domains are very large, then that just it really slows down. So we're currently looking into, okay, what do you do in that case? Can you discretize that domain into fewer chunks and compute some information there? Not clear.
Yeah,
But you've got, compared to standard CP, you're working harder with individual domain values. You have to be careful. If the domains are very large, computation time will just explode. Yeah.
So there's some work on basically using something like Rasmussen's algorithm in a symbolic way, like using algebraic decision diagrams and that kind of stuff. And that seems to scale a little bit better.
For that the estimate. Okay.
Yeah, we can discuss offline.
One very quick question.
So I just wanted to quickly ask if the method, because we've got nice methods for computing the marginals for the constraints that you showed, whether other constraints have similarly sort of nice methods for computing marginals?
Yes, several more. I can tell you those where we don't have. I mean, those, for example, for scheduling, the cumulative or disjunctive, where already, as I said before, it's not one that's easy enough to do. You can't do arc consistency, so you do some filtering, edge finding, and other things, but it's not complete. While counting is even harder there. Yeah.
Thanks.
Thank you. And I believe there is now a social event and possibly a talk by Kuldeep upstairs. If any of you don't have access, the stairwell is near where you go in. We can let you upstairs. And I believe there's also a music night afterwards. Is that going on today?